In this lesson, we'll be looking at mathematical models. In our first example, a rectangle has one corner in quadrant 1 on the graph of y equals 4 minus x squared. Another is at the origin, a third is on the positive y-axis, and a fourth on the positive x-axis. So this point that is on the quadratic is allowed to move, and as it moves, the rectangle is changing its shape and its area. For a better visual, let's look at Desmos. Notice that this point is glued to the quadratic so it can move and it has to stay within quadrant 1. And as it moves, the rectangle is changing its shape and its area. So part A is asking us to find the area of the rectangle as a function of x. We'll start with just the generic definition or the formula for the area of a rectangle, and that is length times width, or we'll use x and y in this case. And it's asking for the area as a function of x. That means both variables need to be written in terms of x. So x is already okay, that's in terms of x. Basically, we need to replace the y with another equation written in terms of x. And if you notice at the beginning, we were given that y is equal to 4 minus x squared. So we're simply going to replace the y with 4 minus x squared. And if we simplify this now, we'll have an area function in terms of x. 4x minus x cubed. There's our area written as a function in terms of x. Next, we'll graph this on the Cartesian plane. So to do this, we're going to use our calculators. So in the calculator, we'll go to y equals and type in our area function, which we found to be 4x minus x cubed. We'll use the caret key that's above the divide to get the 3 exponent and hit graph. And notice my zoom is a little wonky. To fix that, we'll just go to zoom 6, go back to that standard zoom. And here is the area as a function of x. Part C is asking us to find the value of a evaluated at 1. So we can do that in the calculator. Second graph will take us to the table. And if we scroll to when x is 1, we can see that the area is 3. We can do that algebraically as well. So using algebra, a evaluated at 1 is equal to 4 times 1 minus 1 cubed. 4 minus 1 is 3. So we can do it by hand, or we can use our calculator to confirm our answer. The area when x is 1 is 3. Next, we want to determine the value of x that would maximize the area of this rectangle. So we want to try to find the biggest area possible. So going back to Desmos, again, just visualizing it, we're trying to make this blue rectangle as big as possible. What is the x value that would make that area maximized? To do that, we're going to go back to our calculator. Remember, our graph is already there. This is the area function for the area of the rectangle. We want to maximize it. Notice that there is a maximum in our graph. There is a local max here. To find that, remember, we go to second trace. That'll take us to the calculate option, and we're looking for number 4, the maximum. It's asking for a left bound, so we'll scroll over and get close to that maximum. Make sure you're on the left side, hit enter. Then it's asking for a right bound. We'll scroll over to the right side, hit enter, and enter one more time. And it looks like it's giving us the maximum coordinates of that peak in our graph. Keep in mind, the first question is determine the value of x that would maximize the area of the rectangle. So the value of x in this case is roughly 1.15. And then part E is asking for the maximum area. the actual max area is going to be 3.08 if we round it. In this example, we're going to let P, xy, just an arbitrary xy point, be on the graph of the quadratic y equals x squared minus 9. And we're trying to express the distance d from the point P that's on the curve to the origin as a function of x. Notice this one doesn't give you a visual, but if you sketch it off to the side, or if we use Desmos, we can get that. So here's our quadratic. We have this random point P that is on that quadratic, and we're trying to figure out what is the distance from this point to the origin. So notice as this point moves along the quadratic, the distance from that point to the origin is constantly changing, depending on where you are on the curve. Off to the side, we can draw a sketch. This is the quadratic y equals x squared minus 9. And we're interested in an arbitrary point on that curve, P, to the origin. And we're trying to find an equation for the distance between those 2 points. And we know that the origin is located at 0, 0. This point P, remember, is changing. So we have to call it xy, give it an arbitrary name like xy. Now we use the distance formula to find the distance function. D is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. So x2 in this case, we'll call it x. We don't know what the second point is. It's just an arbitrary x value. Minus x1, which is 0, squared, plus y2, which in this case is just y, minus y1, which is 0, squared. So if we simplify this, we get x squared plus y squared all under the radical. So we have a formula for the distance, but it's not as a function of x. We need to rewrite this as a function of x, which means both variables need to be in terms of x. We need to replace this y with another equation in terms of x. Lucky for us, we were given that information at the beginning. We know that y is equal to x squared minus 9. So d equals the square root of x squared plus, we'll replace the y with x squared minus 9. Keep in mind that that is squared. Now let's go through and simplify this. D equals the square root of x squared. Notice that this is a binomial squared, so we can square the first, double the product, it's negative 18x squared, and then square the last, plus 81. From there, we can combine like terms, and I'm going to reorder this just a little bit. X to the fourth minus 17x squared plus 81. Notice now that our distance is written in terms of x. We removed that y variable. So we can say that our distance function is the square root of x to the fourth minus 17x squared plus 81. Now let's find the value of d of 0 and the value of d of 1. If we're doing it by hand, d of 0 is equal to the square root of 0 to the fourth minus 17 times 0 plus 81. That is the square root of 81, which is 9. Hopefully that one makes sense. If this point P is at an x value of 0, it's going to be down here, and we're 9 units away. Remember, we transformed this graph and dropped it down 9 units. Now, if we're using d of 1, we have 1 to the 4th minus 17 times 1 plus 81. That's going to be the square root of 1 minus 17 plus 81, which is the square root of 65. And if we wanted to approximate that so we can check in the calculator, that is roughly 8.06. So now if we graph this in the calculator, square root x to the 4th minus 17x squared plus 81. And check out the graph. There's the graph of the distance. If we want to go to the table and check our answers, x value of 0 means the distance is 9. That confirms our algebra. And then we also can look at 1. We thought it was 8.06, and it looks like it is. The next question is the distance function even, odd, or neither? So this, remember, represents our distance function, and it looks like it's symmetric about the y-axis. And if we have symmetry about the y-axis, that means it's going to be an even function. For what value of x is the distance the smallest? So it looks like we have two places where the distance is at a minimum. So let's go through and calculate those. So we'll go to the calc option, and this time we're looking for number 3, the minimum. We'll have to do it twice because we do have two mins. Hit enter for the left bound, go over to the right bound, and then enter one more time after you guess. And it looks like we have negative 2.9 and 2.5. Notice you have two different values. Make sure you understand which is which. The question here is, for what values of x is the distance the smallest? And it looks like the x value here is roughly negative 2.92 if we round. And if you recall, this is an even function. That means this point should also be very similar, only it's going to be the positive version due to symmetry. If you're forgetting that, we can always go through and double check. Second calc, find your minimum, 3. We'll just scroll over to that other point and confirm that we do get the same value. So left and right bounds, and we do get the same value, 2.92 roughly. And the y value, keep in mind the y value is the actual minimum. So the minimum distance in this case is roughly 2.96. That occurs in two different places at these two x values. So find the minimum distance from P to the origin. That is the 2.96 roughly.